It's a small part. Monte Carlo simulation is a small part in CS1. Much more you will see later. If you see here, Monte Carlo is the name of a place, Monaco. So Monte Carlo here, this is Monte Carlo, okay? It's Monaco. And here if you see, in the city, people normally go, they accumulate a lot of money, they go and they play. Those who are very rich, they go here and they play game of chance, casino. This is famous. We have Las Vegas, we have Monte Carlo. These are the very renowned places. Okay, people go, they have a lot of money, they can go, they can spend, they can win, they can lose. That's where Monte Carlo simulation came. The name came from that. So what is Monte Carlo simulation actually? We need to simulate. We need to simulate numbers. I'll tell you something. See here. Suppose I write a plus b square. You know, this is a square plus b square plus 2ab. Now, if I take 2 here and 3 here, you will see that left hand side will be equal to right hand side. You can check left hand side and right hand side. So this is called deduction. This is one result and we deducted this one. So if this is true, this is the general formula. If this is true, then this must be true. There is no doubt about that. If you are not able to match the left hand side with the right hand side, then there must be some problem. You need to see why they are not matching. So we are going to a particular case from a general case. This is general, this is particular. So always it will follow. This is called deduction. The other thing is called induction. In induction what we do is, suppose I write 1 plus 0 square is equal to 1 square plus 0 square. That is true. This is 1, this is 1. But I can't generalize it. I can't replace 1 by a and 0 by b, so that I will write a plus b square is a square plus b square. I can do this. So we can't go from particular to general. This is called induction. Okay, there is a method how we can go. We can use induction and we can say that the general result is true. If you replace by the numbers with any numbers, that will be true. Here it's not true.
Yes.
This is equal, but this is not equal. So you can go from particular to general, but you can go from general to particular. Now, when you come across statistical models, what normally we do is, you are in the very initial stage. Slowly when you proceed further, when you go deeper and deeper, you will be able to know how really apply statistical methods. Now, what normally we'll do, I'll give you a scenario, just remember. Suppose you want to predict something. This is parametric statistics. We use any formula, any statistical formula. Suppose we'll take a Poisson distribution, or we'll take a continuous like normal distribution. Then we estimate parameters. For that we have a chapter, estimation, point estimation. We'll study more here. Using estimation, using the concept of this chapter, we'll be able to estimate the parameter.
Okay.
And remember, the parameter is estimated from the sample, whatever sample you get. Suppose you get a sample, whatever experiment you are doing, from the sample we estimate the parameter lambda. Suppose lambda you get 5, then you get a statistical formula, e power minus 5 power x divided by x factorial. From this statistical formula you can find the probabilities. It will give you future probabilities. Whatever is x, you need to define this should be the first line. Okay, whatever you want to do, the number of people they go to a particular store, or maybe the number of claims an insurance company gets, whatever is x, you have to define here and you will get this. So you can find all the probabilities. Okay, probability that you will get 10 customers within 1 hour, or maybe 12 customers, whatever way it is. So what we do is we model. What is statistical modeling? In statistical modeling, we come up with a formula. This is not a mathematical formula, this is a statistical formula for a discrete distribution. And we find the probabilities, we find mean value, we find variance, we find standard deviation, all these things we find. And we try to analyze. This is from particular to general. So from particular to general, that means you have the sample. On the basis of sample, we find the future events. Okay, we find the probability of future events, and we find the expected value for future, variance value for future, standard deviation from future. Here also we have expected value, we have variance. These are sample mean, sample variance. These are already existing. We are not interested in those. Using simple formulas we can calculate. We are interested in those. They are the ones we'll do in CS1. Not only expectation of variance of X, there are so many others you will come across. But now, suppose you want to get a sample from a population. Normally what we do is, given a sample, we model it. Model it means we apply a distribution, estimate the parameters, and find probabilities, expected values, variance, all those. Now from a formula, from one formula, any formula like a Poisson distribution, an exponential distribution, a normal distribution, a log normal distribution, from those distributions, how can you find number? Suppose randomly I am writing. Let me write a sample. And I will say, tell me from which distribution I have taken this sample. Suppose I will say 1, then 2, 2, then 5 3 times, then 10 4 times, then 20 80. I will write this. I will say I have taken a sample from one population. Population means population distribution here, like normal distribution, gamma distribution, Poisson distribution. I have taken a sample. You have to say from where I have taken this. I will give you a similar example here. Suppose these are the 3 classrooms. Suppose these are the 3 classrooms. And you are supposed to tell me, I will ask 3 students or 2 students from one classroom. This is 5th class, this is 8th class, this is 10th class. So I call 2 students from some class, and you need to decide from which class the students I called. Sometimes you might be confused because though their heights are more, they look from 10th, they look as if they are from class 10th, okay, but they are from class 5th. Maybe they failed 4 or 5 times, or maybe there is some other thing. So how can you say the students are from 5th class or 8th class or 10th class? Okay, so sometimes it's possible, sometimes it's not possible. What I want to say you here is, sample is there, you have to tell me the population, that means from which class the students are. So here I have given a sample. From sample you have to say me the population, the distribution. In other words, I will give a distribution. Suppose I will give you this distribution, and I will say find a sample from this. Okay, so what you are doing, you are not going from sample to population. Remember here what we did, from sample to population. If you say, I will write here, so normally what we do is from sample to population, like this type. Okay, from sample to population, whatever you do, in more than 90% of the cases you will study how to go from sample to population. From sample, this is called statistical modeling, from sample to population. from sample to population. That means if you go to a new city, suppose you never visited a city like Pune, you go there, you stay for a week, then you come back to your city, then you explain what happened, how are the people, how is the crowd, what is the frequency of the buses, taxis you get there, all those things you can say. But that's your sample. The 7 days you stayed there, basing on the 7 day, you something about Pune. That might not be true. Maybe there is a guy who stayed there for 10 years or 15 years, he or she knows more than you. But according to your sample, you are explaining something, okay? Whatever you are explaining, that is the population. The characteristics about the city you are saying. But what is sample? The little days you stayed. Even if you appear in an interview, I will base the result on the basis of the sample. Whatever answer I got for those 3 or 5 questions I asked you. Okay. If you appear on an exam mathematics in 10th class, then suppose you appeared 100 marks and you get 90, we say that you have 90% in mathematics. You know 90% of what that is there in 10th, 9th, 10th, whatever, or up to 10th class. But it's not true. We have given a sample of questions. Maybe somebody got 70 marks, he knows more than you. But yeah, that's where. So when we predict about population, population means what? Whole. Population means whole. Sample means only sample questions or minimum number of things. So normally what we do is we try to go from sample to population because we want to know, we want to predict. We have seen something, we want to know whether that is true or not, we want to know with what probability that is true, we quantify those, okay, using probability, future probabilities. That is what we do normally.
Okay.
More than, it's not 90%, in more than 90% of the cases we do this. In simulation is the only chapter here you will come across both in CS1 and CS2 where the opposite will do. We'll try to find a sample from a population. Suppose this is 10th class and this is a school, okay? In a school there are students and we need some students from 10th class, okay? So this is a sample. Suppose we have 1000 students or 10,000 students, whatever. Suppose we have 1000 students and we called 3 students. So this is a sample from class 10th of this school. This is a sample, okay? We collected a sample. Suppose you want to know the IQ of class 10 student from this school. You can call 3 students and you can ask something, you can test them, you can give 10 questions, whatever way you can do. Then you can base your result about class 10th. That is what you need to do. So when you take a sample from this one, okay, this sample will simulate the characteristics of population. Suppose I see 3 Indians, I see three people from UK, I call 3 people from US, I call 3 people from some other country, China. They will look different, they will talk different, their behavior will be different, right? So this the sample will simulate the characteristics of population. The sample will simulate the characteristics of population. Even if you see the children, okay, or parents, they simulate the characteristics of parents. So when I say simulation, they will simulate the characteristics of population. So in simulation chapter, though the name of the chapter is simulation, again, why Monte Carlo? Because we are using the game of chance here, okay?
Okay.
They play casino. There is a probability when they play casino in Monte Carlo, the probability is there, okay? The odds of winning, the odds of losing, all those, I'm not going to that. They use probability, that's where it came. The name came from the place Monte Carlo. So in simulation, what we do, we take a sample from a population, that's all. we'll take a sample from a population. But why the name simulation? Because the sample will simulate the characteristics of population. Because the sample will simulate the characteristics of population, the name simulation. But what we are supposed to do in this simulation chapter, we'll take a sample from a population. That's all. We'll take a sample from a population. We have one method here called inverse transform method. Okay, let me write it, inverse transform method.
Okay.
Any doubt by now?
No, sir.
Okay. Now in inverse transform method, suppose you need to know some values of x. The first step is you need to write, and again this is one algorithm, this is a procedure we are using. Proof is not there in our CS1, you need not worry about the proof, just apply the result. Step 1 is, suppose you need to know some sample, okay, you need to write the distribution here. Okay, I'm doing the continuous one now. You need to know f of x of the distribution. Once you know f of x, then you should be able to find capital F of x. There is a formula to find capital F of x. This is the CDF. You need to write the PDF, and from PDF you should be able to find CDF. If you are not able to find CDF, then you can't apply this method. Okay. After that, you need to set u is equal to fx, and you need to solve this and express x in terms of u.
Okay.
You need to invert the function.
Okay. Okay.
Yeah, it's like changing the place position.
Okay.
I'll tell you one example. Suppose I write y is 2x plus 1. Can you revert it? That means, can you express x in terms of y? Yes. 2x will be y minus 1, x will be y minus 1 by 2. So you can write x is, here you can write y is a function of x, y is fx function of x, here x is a function of y, this way. Or if you don't want to write like that, x is a function of y. Okay, so x is equal to f inverse y. This way also you can write, this is a function of y, this inverse we write. Okay, that's what you need to know, that's all. But this is a notation, you need not to worry about this. Because we write u is fx, x will be f inverse u. This is the notation. Once you get this, then you have to write this way. You write x here, sorry, you write u here, and you write x here. Okay, and there is a link between u and x. You can use that to find the values for x from u. Remember one thing that is very, very important. When I say u, this is the u01 distribution, u01, uniform 01 distribution, and you're dependent on u01 distribution if you want to generate numbers from other distributions. Okay, that means you need to know first of all u numbers. You need to know u numbers if you want to generate numbers from other distributions. Whatever distributions you need to generate, you need to know u numbers. If you don't know u numbers, you will not be able to generate numbers from other distributions. For example, yeah, it could be it could be a normal distribution or exponential distribution or Poisson distribution, whatever distribution numbers you want to generate, you need to know U01, not only not UAB, also U01, uniform distribution 0 to 1 numbers you have to get, continuous uniform distribution. So where you get these numbers, you have three choices. One, you can use a calculator. I'll tell you how to use a calculator. And the other one is using Excel or any programming language, R, Python, C, whatever you know. Or you can use a mathematical formula. Okay, there is a mathematical formula also that is not included in CS1. We can use a mathematical formula. Okay, so using that mathematical formula we can generate. There are so many. We will do one in CS2. But you should know how to use a calculator to generate numbers from U01. You must be knowing what is U01. That is uniform distribution from 0 to 1. Remember uniform distribution from 0 to 1? How will be the graph here? This is 0, this is 1, and this is the graph. Okay, this is 0, this is 1. All probabilities are equal between 0 to 1. Okay, I can give you an example. Suppose I called you for 1 hour and I have not fixed the timing, whatever time I will teach. You have some doubts. You called me and you said maximum 1 hour is required for me. So you fixed that, and I prepared my mind that I can give you 1 hour. And I don't know when I will stop. You also don't know. You have some doubts you want to clear. You are asking one by one doubts. And then when doubts are over, I will leave the class. So what will happen is, the time I will spend with you, the time I will spend with you is here. Time I will spend with you. Okay, so Mr. whatever you write, Mr. X will spend to complete a task. This is a continuous or a discrete random variable. This is a continuous random variable because time is a continuous one. So I can stop at any time. I can stop at any time. Suppose 1 hour is fixed, I can stop after 56 minutes 2 seconds. I can stop after 2 minutes 8 seconds. I can stop after 35 minutes 3 seconds. Okay, it's a continuous one. You will not make it a periodic one like 1, 2, 3, 4 like that. Will not make it. So this is continuous, and maximum is 1 hour. So the probability of living, the probability of spending time up to this, up to this, up to this will not change. Okay, so the probabilities are equal, but maximum is 1. This is U01 distribution. Continuous U01 distribution. Remember, continuous U01 distribution. Now, not only this way, we'll also see the numbers, and we'll verify what are the numbers really. These are the 20 numbers we found from U01 using a calculator. Using a calculator, the simple task is random hash, then continuously you press equal to sign. So you will get these numbers. We have taken randomly 20 numbers here. How can you prove that these are from U01? What is sample here? What is population here? This is population.
Yes.
This is a sample. So is there any way you can justify this? Sometimes what happen is, suppose the parents are like this, okay, like suppose 5 feet and 4.8 feet and the child is 6 feet, then it's not true. Maybe you go and you see there are two, there is one, you might see that this guy may be their relative, or maybe their neighbor, or maybe he is a guest. So you have to say something by which I will be this is the sample, and we are doing simulation now. We simulated,
Yes.
in statistical words, we simulated 20 numbers from this population. We simulated 20 numbers from this population U01. But now there must be some kind of a justification. What is the population mean? If you find the population mean here, expected value of x we need to find. If you remember, when x follows uniform distribution and you find the mean value of x, that is a plus b divided by 2. Here a is 0, b is 1 divided by 2. So the mean is 0.5. Mean of the population is 0.5 here. Mean of the population is 0.5 here. You find mean of the sample. If it's not nearing 0.5, there is a problem. And I am 100% sure, if you find x5, it will be near 0.5. Even if it's not near 5, I will not worry. This is a small sample. I can make it 100 sample or 200, 500. The more the sample, the better will be the result. We'll not only check the mean, at least I'm saying mean should be closer. Suppose you find mean x bar, it's around 0.9. How can you say this is from U01? You will not be able to say this will be from U01. Okay, it should be around 0.5, if not exactly 0.5. Still it's not far away from 0.5. If you find 100 numbers, if you find the mean, there where R programming will help you a lot. It will take a lot of time when you use a calculator. When you use R programming in part B, you can find 1000 numbers in 1 second, okay, or maybe in 5 seconds, and you can find the mean in another 5 seconds, okay. And you see, even I will show you in the next class that it's so easy. You go on increasing the numbers, 1000, 10,000, 50,000, the mean will approach towards this. This will lead towards central limit theorem. I'm not going to that, but remember, this is sample mean and this is population mean. At least we can verify this one. That's what I'm saying, okay. So this is a sample. This is a sample from U01. So whatever you are getting from the calculator, there is a formula, and according to the formula, calculator will give the values from U01, okay. And in the exam conditions, they will prescribe you numbers, U01 numbers. See, I started from here. If you know U01 numbers, okay, from U01 numbers, you can generate numbers from other distributions, whether it's exponential or it's normal distribution, it's a binomial distribution, it's a Poisson distribution, doesn't matter. Whatever distribution it is, you have to know U01 distribution, from where you will be able to generate numbers from other distributions. So you have to know this. Now, even if these are not given, you can use a calculator, but in the exam conditions, U01 numbers will be given, because if you use your calculator, I will use my calculator, will give different numbers. So we'll have different answers. It will be very difficult for the examiner to check all the answer scripts separately. So they will give numbers, okay. They will provide some numbers like this: 0.127, 0.218, 0.516. Using these numbers,
Okay.
find numbers from binomial or normal or exponential. Now we are doing continuous distribution. We'll go to discrete distribution later. We have one formula to use, that is called inverse transform method. That's all. So let's do that. Let me write one example. This is the first example. So we'll use inverse transform method to solve this problem. So what we are doing, we want to see three numbers from exponential distribution. Parameter is given, that is 0.1. We want to see, we want to simulate, we want to generate, we want to get a sample, okay. We use simulate or simulation because the sample will uh, behave like a population. Okay, the sample will simulate the characteristics of population. So remember, you need to write, suppose you need to get x numbers, you need to write fx here. So if you want to get x numbers here, we need to write fx. Okay, so what is fx? Fx here is lambda e power minus lambda x. This is exponential distribution. Lambda is given though 0.1, we'll use it later. Then you need to find capital F of x. So you know capital F of x already, I'm not finding. If you want, you can find it also. 1 minus e power minus lambda x. Okay, then you need to set u is equal to fx. So I need to set u is equal to f of x, that is 1 minus e power minus lambda x. Then you need to express x in terms of f. So we'll try to express x, we'll solve it and write x in terms of u. So then what will happen? E minus lambda x will be
1 minus u.
1 minus u. Then you take ln both the sides, log both the sides. If you take log both the sides, if you want, you can write ln also, ln
U.
or log, whatever you want to write. Then x is equal to minus 1 upon lambda ln 1 minus u. Then put the value of lambda. Lambda is 0.10, so this is minus 10 ln 1 minus u.
Okay.
So up to this it's over. Now we'll use the numbers. The numbers are given here. U01 numbers, these three numbers. We'll use these three numbers. Okay, this one, and this one from U01 to generate numbers from exponential distribution. So for that, we'll write a table and we'll use a calculator and we'll try to find the numbers one by one. Now let me write here x. You know the value of x and you know the value of u. Suppose I will write u 0.127. For that I have to find 1x, and I will write 0.506. I will find 1 for this one. I will write 0.819. I will find 1 for this. So what is x? Minus ln 1 minus u. Suppose I want to find the first one. So I can write minus 10 ln 1 minus u. 1 minus u value is 0.127. You can use the calculator. If you observe here, the numbers are greater than 1. If you see here, the range of U01 is 0 to 1. So all the time you will get numbers between 0 to 1 only. But if you see the range of x, because x is from exponential distribution, it's 0 to infinity. So you can get any number here. The range of u is U01.
01.
So you can get all the numbers between 0 to 1. But here the range of x is 0 to infinity. If you remember exponential distribution, here the range is from 0 to infinity. Simulate three random numbers from exponential distribution. We are interested in the exponential distribution. Okay, so exponential distribution range is 0 to infinity, so you can get any numbers, but they are positive. Range 0 to infinity means you will never get negative. Another question I can ask you, suppose you find like this 20,000 numbers. Suppose 50,000 you find, 1 lakh you find, leave every other work. My question is, can you get a number like 5,000 here? Because you see the increasing trend 1, 7, 17. Can you get a 5,000 number? For some of the U01 numbers I will provide you, or you use a calculator, you find it. Can you get 5,000? It's very rare. Maybe if you find crore times, you might get. Otherwise, you will not get that big number. Why? I will tell you. It depends on the distribution. See, when I've written f of x is lambda e power minus lambda x, if you remember, the mean value of x is 1 upon lambda lambda is given 0.1 here, so mean value is 10.
Okay.
That means whatever numbers you will get here, the mean value is 10. Whatever numbers you get here, the mean value is 0.5 u01, but here the mean value is 10. So when the mean value is 10, how can you get a very big number? That is the question. If you see the distribution, exponential distribution pattern, it's like this. That means if your mean is here, mode is here, this is positively skewed. So mean is here, mode is here, means many numbers are here, less than mean. Many numbers you will get less than mean. Very less numbers you will get more than mean. So more than 10 you will get less numbers. Less than 10 you will get more numbers. If you suppose you find 1000 numbers, more than 500 will be less than 10. Okay. And it will not go drastically. If you take this lambda is 0.00000001, your mean is high, then you will get. Okay. In this problem you might not get. That's what I am saying. Again, that is something we'll not worry. We'll just see that the range is 1 to infinity, we are not getting 0 to infinity, we are not getting any negative number. And we'll also check the sample mean with the population mean. Population mean we know 1 upon lambda, that is 1 upon 0.1 here, that is 10. And we'll see if this is around 10 or not. 17, 7, 24, 25 divided by 3, 8 point something. Okay, this will be 8 point something. So yes, you are getting around 10. If you take suppose 100 numbers here, you find the mean, maybe it will be close to 10. We can verify that also using R programming easily. Got it what I am saying?
Yes, sir.
Got it what I am saying?
Yes, sir. Yes.
Okay. What I am saying is, with three numbers are not sufficient. Suppose there are 10,000 students in a school. I call 5 students, I check their IQ, their mean IQ I will find, sample mean IQ, and I will say the sample mean IQ of that particular school is this. That is not true. I have to take a bigger sample. The bigger is the sample, the more the sample, the better will be the result.
Okay.
3 or 5 if I take, that might not be sufficient for a school where you have 50,000 students or 20,000 students. I need to take a bigger sample. So you have to take a bigger sample. Instead of taking 3, you can take 30, 100, 500 and you check whether the mean is approaching towards 10 or not. If you take more, definitely it will go towards the mean, population mean. Sample mean will go towards the population mean. Otherwise there must be some problem in calculation that we need to verify. So this is from one distribution.
Okay.
Inverse transform method has limited scope. There are other methods, but in CS1 we'll use only one, that is inverse transform method. We'll do some problems where inverse transform method will not completely help, but from using this one you will be able to do the problem. Okay, little bit deviation will be there, you will be able to know from the problems. But directly if you want to apply, remember you should be able to not only find f of x. Suppose I give a normal distribution, you can find f of x. If I give a gamma distribution, you can find f of x. You don't know CDF of a gamma distribution, so inverse transform method is not applicable. Even if you are able to find f of x in some distribution, if you are not able to invert this, it's not that all the functions you will be able to invert. Not possible.
Okay. Okay.
Yeah, it's not possible. Suppose I will write e power square root of x plus x square is equal to 2y plus 5 sine 2y plus 5, or I will make it very complicated, something like this. And this is the equation. I want you to express x in terms of y. Okay, or maybe I will write y here, y is equal to y in terms of x. I will tell you to find x in terms of y. It's not possible. You can't invert every function. It's not possible. Even I can write this one. I will write this one. Y is equal to x cube minus 3x plus 7. Express x in terms of y. You can do this one. Okay. So inverting is also required, which is not always possible. So it has limited scope. I've given one example, and simple examples are here where you can find the numbers. Now we'll go to the discrete distribution. This is about continuous distribution. So let's go to discrete distribution. We'll consider one discrete distribution. I'll write 1 to 3. Then the probabilities I will write 0.7, 0.2, 0.1. Total probability is 1. This is a discrete distribution. And you want to simulate numbers from this. So what you need to do is, this is not fx here, this is small. Again we are using inverse transform method. So we'll find capital Fx, that is up to. So now up to 1 this is 0.7, up to 2 this is 0.9, up to 3 this is 1. Total probability is 1. So this is cumulative. Cumulative means probability up to 1, that is 0.7, up to 2, that is 0.9, you need to add, up to 3 you need to add everything. Okay. Now it's like this, except we'll write except 1 if u is between 0 to 0.7. If you get u between 0.7 to 0.9, then except 2.
Okay.
Except 3 if u is between 0.9 to 0.1.
1. Okay.
Yeah, let's do it first, okay? Then I will let you know why this. You can, if you want, you can use equality somewhere. It's a continuous distribution, will not worry. Now you tell me some u01 numbers and we'll see how to generate numbers from this. Acha, before doing that, if I tell you to generate 100 numbers from this distribution, this is the example, okay, 100 numbers. Can you tell me some numbers? The numbers will be 1 to 3 only, the probabilities are given, right?
Yes, sir.
Suppose you ask me when is the next class, I will say I don't know, I just reached, I am planning everything. Your class will be either Monday, Wednesday or Friday. So answer will be Monday, Wednesday or Friday, that's all, right?
Okay.
If you have a die, you roll it, the probabilities are 1 by 6, you will not get a 7, you will get either 1 or 2 or 3, 4, 5, 6, right?
Okay.
So you are correct, that's what I was expecting from you. The numbers will be 1 to 3 only, okay?
Okay.
But how many ones you are expecting from this distribution? Suppose you will do 10 times. 70% chance of getting 1. It's not a die equally likely. The probabilities are not equally likely. One chance is more.
Yeah. 70%.
Yeah. Suppose you need some cash from me and you call me, I want to go to your place, keep ready some cash. I'm saying there is a high probability, 70% probability that I will give you 1000. There is a 20% probability that I will give you 2000. There is a 30% probability that I will give 3000. I don't have much cash now. So if you come every day in the morning time, someday you will get something, but you will get either 1, 2 or 3. But chance of 1000 is more, 70%. Let's see that is reflecting or not. So now you have to tell me the u numbers and I will see this. See, I'm giving you have a I'm giving a very high interval for 1. Okay, you tell me, you just tell me u01 numbers from calculator. One plus 1 plus 1 plus 1 plus 1 plus 3 2 2 2 2 divided by 10, right?
Yes, sir.
What is that? 3 to 5 to 7 to 9 to 11, 12, 13, 14, 15, 16, 1.6. Sample mean is 1.6.
6.
Now, if you find the population mean, let me find the population mean here. .5. See, they are so close, right?
1.4. Yes.
1.5, this is 1.6. That means if I change only 1 2 to 1, suppose this is 0.778, if I get 0.678 by chance, it will be 1, and then this will be exactly equal to 1.5. That means whatever way I expected, 70% ones, out of 7 ones, 1 2 3 4 5 6 7, I need to get 2 ones actually, not 1 I think this should be 1.7, okay, or whatever. I can check once again. 5 here, 5 3 8, 8 to 10, 10 to 12, 12 14 16, 1.6 I got. Okay, that's fine. So if I get 2 ones here, I expected to get 7 ones out of 10 ones, 2 twos, 1 3. I got 1 3, that's fine. I got 2 twos, that's fine. Instead of 7 ones, I got 5, but I got 2 twos. If I get 2 ones, then exactly whatever way I expected, I will get that way. Whatever way I expected here, that way is my sample. But it will not always be, okay? It will not always be whatever way we expect. There will be a little bit variation. When you say the expected time to reach from A to B is 10 minutes, sometimes it will take 8 minutes, sometimes it will take 11 minutes. So sample is different, population is different. Population is expected value, that will never change. So you do every time, you will get different samples, you will get different sample means, but population mean will not change, that is 1.5. Again, if you take sample many times, you find sample means, mean of those means, that will be equal to population mean. That is central limit theorem. Again, I am not going to that. So this is about simulation. Okay, that's all.